super-Earths. These terrestrial worlds are defined by their mass, which sits comfortably between that of Earth and giant icy planets like Neptune. While our own solar system lacks a representative in this category, they are incredibly common throughout the Milky Way galaxy. Astronomers look for them within the circumstellar habitable zone, the sweet spot where stellar radiation allows liquid water to persist on a solid surface. Because they possess higher gravity than Earth, these planets can retain thicker atmospheres, which may provide better shielding against harmful cosmic radiation. However, their larger size also means their internal heat takes much longer to dissipate, potentially driving prolonged, intense volcanic activity that could dramatically alter their atmospheric chemistry over billions of years. Notable examples include Kepler 452b and TOI 715b. For me, with all that gravity and volcanic activity, the local seafood probably comes pre-cooked. Desert worlds. Also known as arid planets, these dry environments possess extremely limited water supplies compared to Earth's vast oceans. Climate simulations suggest that these dry worlds might have broader habitable zones than wet, ocean-covered planets. With limited surface water and reduced water vapor feedback, a desert planet may maintain stable surface conditions across a wider range of distances from its host star. Water on these worlds may be confined to small oases, underground aquifers, or polar ice caps, mimicking some of the most resilient ecosystems found in Earth's own extreme deserts. Their potentially thinner cloud cover may allow astronomers to study their surfaces and atmospheric compositions with fewer visual obstructions. Examples include Mars and exoplanets like Gliese 12b. No water simply means no fish, so this dry rock is a complete waste of my time. Ocean worlds. These planets are thought to be largely covered by global layers of liquid water, with little or no exposed dry land. Astronomers describe them as worlds where water may make up a significant percentage of the total planetary mass, far exceeding Earth's fraction of a percent. Without exposed rocks to weather, these environments may lack the traditional carbon-silicate cycle that stabilizes Earth's long-term climate, meaning their atmospheres may rely on different chemical feedback mechanisms to remain stable. Deep beneath these global seas, the immense pressure can compress water into exotic phases of high-pressure ice, physically separating the liquid ocean from the rocky mantle beneath. This unique layering presents a fascinating puzzle for astrobiologists as it limits the direct interaction between minerals and water that is often considered important for the emergence of life. Notable candidates include TOI 1452b and Kepler 138d. Well, it has plenty of water, sure, but drilling through high-pressure ice just to go fishing sounds like way too much work. Exomoons. These are natural satellites that orbit massive gas giant planets located within a star's habitable zone. While the giant host planet itself lacks a solid surface, its moons may experience conditions capable of supporting liquid water and atmospheres. These bodies can receive energy not only from their parent star, but also from reflected light, thermal radiation, and tidal interactions associated with the gas giant they orbit. Furthermore, the immense gravitational pull of the giant planet stretches and compresses the moon's interior, generating internal tidal heating that may sustain subsurface oceans even far from a star. This expands the definition of habitability beyond independent planets. Possible candidates include Kepler 1625bi and Kepler 1708bi, which astronomers have proposed as possible large exomoon candidates. I absolutely hate gas giants because you can't land on them, but if these moons have oceans and fish, I guess I'll let it slide. Superhabitable worlds. These hypothetical planets are theorized to be even more suitable for life than Earth itself. They are typically 10% larger than Earth, meaning higher gravity that creates a more archipelago-like geography. Without massive, arid continents, their surfaces feature shallow seas dotted with island chains, creating highly nutrient-rich environments. These worlds revolve around K-dwarf stars, which are cooler, less volatile, and live tens of billions of years longer than our Sun. Representative candidates include Kepler 442b and KOI 5715.01. With all these shallow seas and islands, this isn't a planet. It's just a giant, all-you-can-eat fish buffet. Coreless planets. These theoretical worlds form without a distinct metallic core, leaving most of their interior composed of a massive rocky mantle. This unusual structure may occur when a planet forms in a highly water-rich environment. causing much of the iron to oxidize and remain mixed within the mantle instead of sinking into a central metallic core. Lacking a liquid iron interior, they may be unable to generate a strong traditional planetary magnetic field to shield themselves from space radiation. Despite this vulnerability, if the planet is massive enough, a dense atmosphere could still protect the surface and preserve potentially habitable surface conditions. Finding a confirmed example remains extremely difficult. Trying to fish on a planet without a magnetic field sounds like a terrible survival strategy. Carbon planets. These theoretical worlds may form in protoplanetary environments where carbon is more abundant relative to oxygen, potentially altering their internal and surface chemistry. Unlike Earth, which is dominated by silicate rocks and oxygen compounds, a carbon planet is theorized to feature crusts rich in graphite and carbides with potentially deep layers of diamond-like material. Water on these worlds may be highly scarce, chemically altered or locked away, while liquid hydrocarbons or other carbon-rich compounds could potentially exist on the surface. While finding a definitive carbon planet remains difficult, astronomers have proposed several intriguing candidates. For instance, 55 Cancri A was once hypothesized to possess a carbon-rich interior, and Pulsar PSR 12 57+12 could contain unusual carbon-rich compositions. But I don't care how many diamonds are buried underground. Zero water means zero fish, so it's a hard pass. Double planets. This term generally describes a binary planetary system in which two planetary bodies of comparable mass orbit a shared center of mass. If such a binary pair resides within the habitable zone of their star, both worlds could potentially develop atmospheres and maintain conditions favorable for liquid water. The close gravitational relationship between the two bodies may generate tidal forces capable of influencing internal heating and geological activity, potentially prolonging geological activity on both worlds. From the surface of either world, the companion planet could appear as a massive and detailed feature in the sky. While no confirmed habitable double planets exist, Pluto and Charon are sometimes discussed as a dwarf binary system that demonstrates strong gravitational interaction between two closely bound worlds. Two planets sharing the same sky just means twice as many places to go fishing. Hycean Worlds. This proposed class of exoplanet differs significantly from traditional Earth-like environments, potentially featuring global oceans beneath thick, hydrogen-rich atmospheres. The immense atmospheric pressure exerted by these hydrogen envelopes may allow liquid water oceans to exist even at temperatures that would normally vaporize open water on Earth. While candidates like K218b show promising atmospheric data, their true nature remains actively debated. Some models suggest these worlds might harbor deep oceans, while others indicate they could instead contain magma seas or supercritical fluids where no stable surface exists at all. Their potential habitability depends on a delicate balance, as overly thick atmospheres could turn these planets into extreme greenhouse worlds. At those temperatures and pressures, the fish might already be pre-cooked before we arrive. Rogue planets. These nomadic worlds wander through the darkness of interstellar space without being bound to any parent star. Formed in ordinary stellar systems, they may have been ejected during early gravitational interactions within their planetary systems. While they lack sunlight, planetary scientists have proposed that rogue planets could potentially maintain habitable environments beneath their surfaces. If a planet possesses a thick atmosphere or a heavy layer of surface ice, it may be able to trap internal geothermal heat. This insulation could allow subsurface liquid water oceans to exist in perpetual darkness. Notable examples include the free-floating planetary mass object PSOJ 318.522 and the rogue planet candidate OGLE2016BLG1928. Having a secret ocean trapped under pitch-black ice just means we'll have to invent glowing fishing lures to catch anything. The universe is vast, hostile, and in many places catastrophically poorly designed. Authorize future planetary analysis transmissions by subscribing and enabling notifications. My search for the perfect aquatic ecosystem continues, and frankly, I'm getting hungry.